So why does it why this memory profile actually matters? As I've already said, GPU have limited RAM. So the challenge is during training, you not only have to fit all the model weights, you also have to store the activation values and also gradients and optimizer for training. So training is actually much more expensive than running the model and of course only storing the model. So for a bird like half a billion 0.5 gigabytes model, you need approximately 2 gigabytes of activation. So during the forward pass, so you have to store all the forward pass and also all the gradients as well during training. So if you want to train your own large language model, you have to do the calculation first. And make sure that it can fit into the 16 gigabytes of memory. So for the model size, as I've discussed, you have to multiply by 4 bytes, which takes up about half a gigabyte. And during training, you also have to think of the data. So even if you are doing one-by-one training, the data is also going to be large. But of course, in a more practical sense, the batch size or the number of data in a single training should be more than one, around 32. Okay. So for training a large language model, you have to do some extra calculations. Of course, the model weight, the input data, so the batch of the input tensor. So the data will be converted to tensor during training. And of course, the number of activations and gradients and optimizer states. Okay, can I ask anyone of you can record what the activation are and why does it stored requires 2 gigabytes of memory during training? Anyone can record from the last semester why there is a activation memory taken over during training? Okay, so first of all, anyone know what the activations are? Okay, so during training, okay, let me have a brief overview. So now you are going to train your own large language model, correct? And you have to store your model weights inside a GPU. And of course, you need some data to train your model, correct? But why do we need something like activations, activations, which takes up more than the model size? Why? So what is this part? Anyone recall from your last semester? No. Anyone know what are activations? Okay. Okay, so maybe I will remind you what you have learned. So okay, so remember this diagram. So we have input layer, we have output layer, we have input layer, we have hidden layer, we have output layer. Anyone know where's the activation value? Okay. 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 So now maybe I will have. So the activation values is actually when you have one input and you have a neuron, and the value will pass on to the next hidden layer. Before the next hidden layer, we have an activation function. Okay. Okay, so recall this activation function. We have okay, we have different activation functions, right? We have logist, we have relu, this one relu, remember? Relu activation functions. Oh, remember you have the alpha AI robots, right? Okay, good. Okay. When you view the network model, we have a input and weights and plus bias and then multiplied by an activation function, correct? Okay, so after the activation functions, so input weights some activation functions. This is multiplying together and then output. So during back propagation, remember back propagation, we have to get the error from the output and then back propagate to change the weight, correct? Okay. So because we have to store all the activation values and be able to update the weights, therefore in here we have to store all the activate values. That's why when you are training a model, we have to store all the activations. Okay? So this takes up I think around 4 times of the actual model weights. Of course, the gradient, you need to know what, because does anyone know why the gradient size is the same as the model weights? No? Okay. So because for each weight, we have to update the value with the gradient. Remember back propagation. So you back propagate the error back to the gradient. And of course, we have some optimizer state, which is the similar size of the activation. So for training a 0.5 gigabytes of model, half a billion parameter model, we have to use around 5 gigabytes of memory. So here is the diagram. The activations equals the output from each layer during the forward pass and kept for back propagation during training. Okay. So because back propagation needs activation to compute the gradients, record the gradients, we need x times the delta loss and delta c to delta z to compute the actual update value. So if you forgot all about that, make sure that you review the Alpha AI robot. So go back to the Alpha AI robot slides, and you will remember why do we need all these activations. Okay. So the bird actually have the transformer layer, right? When you actually do the self-attention, the matrix size is the self-attention memory will take up the batch. So this is the data batch that you're passing into the neural network. because bird itself is a multi-headed attention layer. We have 12 heads, and also we have the attention matrices. So in total, it will take up around 400 megabytes per layer, and we have 12 layers. Okay, so after you run the script, you should see. Let me check out the output of this script. So memory profiling. So when we do memory profiling, we try to create some tensors and check out the memory usage of the GPU. So we have 14 gigabytes of free memory, and after creating the tensor, it takes up to 0.1 memory of only a 1,000 by 1,000 dimension tensor. And of course, if you do sequential allocations, like allocating tensor by tensor, the memory size will stack up. So if you ever come across why I'm loading such a small model but take up so much memory, because some code in your Python script may be wrong. So make sure you do in place. So replacing each matrix each time when you are doing the operations. So how to do this in PyTorch? How to do in-place memory in PyTorch? It's actually fairly simple. Okay, you do add this dash line after the operation. This will make all the operation in PyTorch being in place, which means the memory won't stack up after each operations. Okay, so when you do vibe coding, please add this into your prompt in place operation when you do vibe coding. Of course, I won't be expecting you to write actual Python script. Of course, we are going to use AI to generate, but make sure that you put this in your prompt. Okay, so of course, as I've mentioned before, different data types impact memory. If you're running out of memory, be sure to change the memory type from floating point 32 to floating point 16, which halves the memory. Okay. So for a transformer, you can actually pre-compute all the memory that needed layer by layer. So these slides are for your reference when you are doing your project. QKB projections for a bird is around, these are the matrix dimensions that you can refer to. Okay. So in a bird model, there are 12 layers. The batch size would be 32, standard batch size. And the attention matrix, attention score would be 512 times 512. So by looking at this, can anyone tell me what's the context length of this model? The context length of this model? Context length. Does anyone know what a context length means? Okay. Context length is有对的答案啊 Okay. So someone actually what the context length is. So is the maximum size of your large language model, right? Okay, that's great. So does anyone know what the context length is by looking at this model? Context length. So you have these numbers like 7, 6, 8, 32, 12, 512. Okay. And other numbers like, of course, this does not look like context length, but you do have like 3072. So if you think context length is 768, please raise your hand. No? Okay. Okay, 1, 2, okay. 32, raise your hand. No. 12, raise your hand. No. 512, raise your hand. No. Okay. Okay. So the context length is actually, let me give you a hint. The context length is actually should be the same size of the attention matrix. Record the attention mechanism, right? Self-attention mechanism. So recall this self-attention mechanism. You attend every single word with another every single word, correct? So the context length must be the row and the column of the actual matrix, because you have to relate each word into all parts of the sentence, correct? Because the model must know all the relationship between all the with all other words. So the context length must be 512 long, because this is the attention matrix. You know this is the attention matrix because this part makes up the square matrix that you see in attention, because you need to know all the relationship against all other words, right? Or all other tokens. Okay. So the attention score will take up, this is the batch memory size, this is the number of attention matrix that you have. 512 times 512 is the context length, and this is the context window that the model can understand. Okay, so the each bird. Okay. Oh, sorry. This is 12 heads, so it's multi-headed attention matrix. Okay, not 12 layers. Okay, so per layer you will have 12 of these matrix, which will taking up 380 memory per layer. Okay. It's just so that it's just a coincidence that the bird layer also have 12 layers. So for each 12 layers, you multiply by around the hidden state, and you get the 600 megabytes of stored activations. Okay. So total training, you will need 400 megabytes for the model. The activation, you need 600 megabytes, and also the gradients, you need to store same as the model size, and also the optimization states. So around 4 to 5 gigabytes per you need 4 to 5 gigabytes VRAM to train a half a billion parameter model. Okay, so you can refer to these slides at home, and I just want to talk about a concept called memory leak, which during your vibe coding you can add this to check your code whether it will have some memory leak or not. Memory leak refers to the memory that is allocated but never freed. So even though you are not using the actual memory, a bad coding example is if you append the results, keep appending the results to the tensor, you will get the memory scaled linearly. And so a good practice is to, after each iteration, you delete the tensor after using it. Okay. To summarize, in order to save some memory, you can have the precisions, reduce the batch size, clear unused tensors, and use smaller models and avoid memory leaks during the training process. Okay, so this is the comparison of the training memory needed and the actual, if you are just running the model. So you need around 10 times the memory if you're training the model. So in here, when you have like 14 gigabytes of VRAM, so you have to make sure that during the training you can actually train your model. Otherwise, you have to do some mixed precision training. So if you reduce this, you can cut the memory by half. Okay, so any questions? Okay, so now you have the model and you know how many RAM that you will need to train an actual model and do the inferences. We are going to talk about data, because usually the data will be very large. Okay, let me click into this one. Okay, so usually this data set is called the contents of colossal clean corpus, a massive web-crawled data set used for retraining large language models like T5. So in here, you might want to know how large the data set is. It's so large that sometimes you cannot fit all the memory into the GPU. Okay. So the C4 dataset is around 13 terabytes. So what you can do is use streaming for large dataset. The code is essentially streaming dataset. When you're loading a dataset, you do not load the entire 13 terabytes of data into the RAM. Instead, you stream it parts by parts and then train it and remove the data and so on. So that's how you train large dataset with limited resources. Of course, if you have unlimited resources, this may not be your problem, but in this course, if you want to train from this dataset, you must use a low dataset and you set the parameter to streaming. So in vibe coding, you need to know this because you need to tell the AI to set it to stream. So actually, this is all I want to talk about for the memory, and you can go through these slides. It's essentially just talk about how to load different data set, like load all images, or using a library to load all the images. You can run this script, and the results will be cached in the directory. Actually, I preload some data set in the HPC server, so it should be you should be using the cache. If not, you can still have the permission to load the data set in. Okay. So loading text data set from 1,000 examples from a movie reviews, IBDM took around 5 seconds. And after loading the data set, you can use these kind of code to view what the meaning, what the data set actually looks like. And these are some useful programming code that you can use for training. So shuffling the data set during training. Because the script I provided for you is actually load the first 1,000 examples. So the first 1,000 examples are all used. Because the database is sorted by labels. So make sure that when you're downloading data set or half of the data set, you need to use this shuffle command to load the data set. And image data set, you can use it in your project. Make sure you understand the dimension. For images, there is an RPG channel, so extra memory that you need to actually load the image. And you need to understand the class distribution of your data set. Make sure that it is evenly distributed. Of course, this is the most important part, is that you stream the data instead of directly load into the GPU. Okay. Of course, save your progress before. Make sure your code has some saving progress kind of mechanism, because if it is ran more than 8 hours, it will automatically stop. If you need to train your model more than 8 hours, say for a week, we can organize that, and I can set the time limit a bit longer. But you need to know, make sure that you save all the process the data. Okay, so tokenizer pipeline, we will do this in a second. Okay, so any questions before we go to our main course today? So tokenization, machine learning to read. Just a quick review. How the large language model actually reads is actually only reading the token ID. So how do we convert a large text corpus to tokens? We use a tokenizer. One approach is to break each word into a token, and the other approach is to break each character into tokens. So any other way to break the words into tokens?
Segments of words.
Okay, good. So you remember. So segments of word, right? When you view the GPT-3 tokenizer, it actually breaks the segments of words, break a word into different segments, commonly known as the byte pair encoding. So the vocab size of, say, if you're breaking the word into tokens, you need millions of tokens. If you're going to break the character, if you use the UTF-8 encoding, I think, if I remember correctly, it's 2056 character. Okay. And if you use some word to break the corpus into tokens, you have control of the vocab size. So you control this number. So you can set this number to whatever you want if you use some word. Actually, this is not a new concept. It's invented in 1994 and it's adapted for NLP in 2016 and used by GPT-2, 3, 4, BERT, and also Llama. So the core idea is to start with characters and then find the most frequent pair and then merge them into new tokens and repeat the process until the vocab size is big enough. Okay, so let's do a quick example. If your corpus only have 3 words, so first of all, the first step is to break into a set of characters, so a dictionary of characters, and then you count the frequency, right? So for L in here, there are 3 L's, 3 O's and 3 W's, 2 E's, 1 R, 1 S, and 1 T. Okay. And the most frequent top 2 frequency should be L and O. And then you find what's the, so there are 2 kind of combinatorics that you can find, like for the pair. So LO, but you can only find the LO pair. So LO pair appears 3 times. Then you merge the L and O character to create a new subword unit. So the corpus now becomes LOWERST. Okay. So we create the new token for LO. And then you repeat the process, find the most frequent pair again. The most frequent pair appears to be LOW, and the LOW will become the new token. Okay. So now, repeat the same process. When you're repeating, the vocab size would be LO, and then you have the new, this is the frequency, and this is the vocab size, until you have the desired vocab size. So we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, the vocab size. You can pick this number. So how large you are going to stop until say 10K of vocabs. So this is the BEA algorithm. So the insight is you have the frequent words become single token. So the become a token. And also you can handle like unknown words. Like if you have misspelled something like this, you can kind of break it down. That's how the large language model understand your your typo, and also it's domain adaptable, and we can try this out in now. Okay, so let's build this tokenizer. So your mission is to train 3 custom tokenizers, not actually train, but actually make a tokenizer and compare them with the GPT-2's tokenizer. And you are going to analyze which works best for each domain. So we have 3 domains, medical, legal, and general. So in lab 1, I've prepared some sample corporates for you to train 3 separate tokenizer. So medical corpus, it will have some sorts of medical jargons. legal corpus will have some kind of legal terms, and some general corpus will just have some general terms of AI. Okay. So let me go back to that. So this is the folder structure. This is the PEA trainer Python, and we have like comparison analysis. So for you to compare the results and also sample corpus, and also test terms, I have created one for me to run as a demonstration. But this is the actual code. It won't take I think 15 to 20 minutes to run. I think it only takes something like 5 minutes at max. Okay, but because you are running it concurrently, so it might take longer. So in order to run the code, the same idea is to go to the directory. So go to the directory. Oh, I think I've missed one step. Can anyone know what the step that I missed? No? Okay, I have missed one step in this slide. Anyone can figure it out what step that I missed? Anyone? Not creating lab one, no? Okay, so record so remember the CH mode that you have to type each time you run the shell script. You have to make it an executable for you to run any script. So the step that I missed in this slide is the CH mode plus X. Okay, so you have to make the run or the run lab executable before you can submit the script. So it should be chmod and also chmod run lab 1. So let me explain the code a bit. So the code that you're going to train your tokenizer is actually using the BEA trainer, the tokenizer. So record special tokens, you can define special tokens. Padding, which means you want to pad you want to have added to your tokenizer for the bird training progress. Anyone know why do we need PAD token? Why do we need to add special token of a pet? Why do we need? Okay, you can actually look up what these tokens are. So okay, so remember the model whisper that we introduced in the first semester. We have special tokens in here called PREV3, no speech, VAD, and also other special tokens like DOT. Remember this? Why do we have to add PAD for the special tokens? I think Lou Chuan, hi, you have mentioned this earlier, so I guess you might know the answer for this one. Why do we have to add PAD in here?
大概的意思是不是就是我们设立了一个专有的这个 token 之后，就可以批量式的去计算，所有跟它相同的这个 token 的就可以减少它的 GPU 的这个饭量，然后可以批次的计算。
Okay. Okay, no. You have mentioned the token, the context length. Remember, it's actually when there is a text, it's shorter than the context length, but you have to feed all the matrices into the model. You need to add the padding token. Essentially, this works out for when you do training and you do batch processing, you need to have the matrix in the same size. Remember, you do matrix multiplication, you do each row, each column, and the matrix size would be fixed. Because when the context length varies and the data length varies, you need to make sure the matrix multiplication also aligned with your model. So these special tokens is for aligning the length. Okay, so there are other special tokens for separations, CLS, and also unknown vocab. Okay, so and then how to train a token is essentially using the text. So you can just feed the tokenizer with a file that you have scraped from the internet, or you created your own script. So when you are doing your project, please make a text file in the sample corpus and train it with this code. So now you know how to change the code and to train your own tokenizer. And of course, you save the tokenizer, something like medical tokenizer JSON. It will return for you a JSON. Of course, you can call the GPT-2 tokenizer to encode some text. So I have trained a medical tokenizer which encoded this myocardial infarction. So a very difficult medical term. Using GPT-2 tokens, it takes 8 tokens. So it will be considered to be inefficient. When you can have specialized token, you only need 2 tokens, which is actually 4 times better. So fewer the tokens, the better, because you can use less computation power to achieve the same same computing with the same GPU. So medical terms, some legal terms, some general terms. So the hypothesis is that we might be able to train a tokenizer better than GPT-2 in some special domain. Okay, so first of all, the fewer the token is the better. And then the main code for training is that you can set the vocab size. So for it's much smaller vocab size, or you can actually increase the vocab size. So training, you can train your own. You can train your own corpus, and so the results will be saved if you are setting the vocab size into 5,000. In here, the results will be saved in medical pipette encoder 5K. Okay, so in this lab, the vocab size are 10K, 3K, 5K, but the corpus is not that big. It's only around 100 centimeters. Okay, so when you see something like this, the demo, when you're looking at this table, which word is our customizer do better than GPT-2? Of course, I write it here. So this term, but some terms is actually worse, like this one. So it only takes like 5 tokens for GPT-2. It will also generate a graph, so it will have some kind of, it will get you a better understanding of how the tokenizer performs in comparing to the standard tokenizer. So the token per term, you can compute this. This is the lower bound, upper bound. This is the confidence interval, and also the mean. And you can view the distributions. Of course, the lower to when the distribution shifts to the left, it is actually better because it uses fewer tokens. Okay. So again, if your custom tokens count is larger than the GPT token count, that means you should use the GPT token count because it is actually worst. Okay, so let's train our first tokenizer. So the training forecast, the training code is actually so when you run this, the training progress will start, and you can view your training progress. So let's put this together now. Let's see. Okay, so now I have 2 jobs running. One is okay, so run is 153. So let me check my status. Yes.
第二第三行跳緊你睇唔清應該係呢個，因為呢睇先，應該呢兩個加 x one underscore demo dot s demo dot s 睇下加 x one underscore lab 1 dot s。
Okay, so these are my results. You might want to download it to your folder. Okay, so when you click outputs, so in here in lab 1, you can click download here. and you can get all your results. And then when you extract all the results, and you will have your tokenizer, and you can view how the tokenizer performs. So I will sort this by type, and here is all the graph that I can see. So in your report, you
咁兩個啊，之後再打翻
generate
嗰
source of
個
graphs,
Spatch 嗰個
view
即係呢
the
兩個
performance of all the tokenizer. So just a quick view of the tokenization.
佢係嗰個裝
So let me explain how to read this graph, right? Okay, so in this graph, the GPT-2 tokenizer used 7 tokens to kind of decompose this word. But our custom tokenizer only uses 1. This shows our tokenizer is actually better than the standard one. So in your report, you might want to state this very clearly. So it actually performs better than the standard one because you focus on the medical corpus.
skill hyphen U
And because this gives you an overview of a bunch of text that you want to have a look. So the vocab size of the tokenizer is 5K, so only 5,000 vocab. So your model will only need to read 5,000 vocabulary. Also, your embedding model will be much smaller because you only need around 5,000 vectors for your model. So in here, you can see the tokens per term. Our medical tokenizer is actually only, I think it's doing worse than the GPT-2 because of, you see the the lower bound is actually better. So we have a good lower bound. But the upper bound for say some challenging words, you still need 14 tokens per term. And also, the mean is higher than the GPT-2. So in some areas, we perform better. And for this distribution, you can really see for some terms, we can, for some areas, we are better than GPT-2. But however, in these sorts of areas, we are worse than GPT-2. So this is general corpus, it's not medical terms now. With 10K of vocab size, I think we are doing generally worse than the GPT-2 for general terms. So the token count per words, I think is actually worse than GPT-2. You can see it here, please. Okay, now this is a vocab size for general corpus for 30K vocab, and still is not performing better than GPT-2 in general corpus. Okay. So in 50K, I think the performance is similar. Not much big difference in general corpus. Okay, now for legal terms. Legal terms, I think GPT-2 trained it's actually quite good in legal terms. But for some legal terms, in some area, we still have an edge. So if you're pitching investor in models, you can say in some areas our model is more efficient than the GPT-2. So you can highlight this term. And of course, you can see the distribution here. 30K, 50K, I would say not much different, only a slight niche. You can see in here. Okay, medical corpus seems similar. We see similar patterns. Okay. So this is the overall results where you can visualize how our tokenizer perform against a standard model. So in your project, I want you to think of a niche that you might want to train your model in and try to train your own tokenizer. So why do you think our corpus is not as good as GPT-2? What have I not done, or what have I not done right? Yeah. What have I not done right? I only outperform GPT-2 in some specialized area. Okay, so when you look into the actual vocabulary, we only take, I think, a minute to train the tokenizer. So the sentence of GPT-2 actually trained on a much larger corpus. So you can see in the BPE algorithm, we actually need a large corpus to kind of encode for better tokens. Because if you go back to our algorithms, the critical point of this algorithm actually relies on the number of iterations or the vocab size you are going to make, and also the corpus, the corpus size of the actual training. So when you start, you might want to start with a large corpus, because when you start with like 3, not even all the alphabet are included in here. So that's why you want to start with a much, at least include all the alphabet when you're starting, or include some other punctuations as your base vocab size. Okay, so now I will give you some time to work on your project and find a corpus and try to train it in the HPC server. So I will give you some time to find a corpus around of your niche, and also have a brief discussions on the topic that you want to do, and try to train your own tokenizer during the lesson. So I have reserved some time for the consultations, and if you want some advice in the project, and also, or you want to advise on what kind of model that I want to train in this course, please feel free to ask. And okay, so I'll give you say 10 minutes to find the corpus of your specialized area and try to train it in the server. Okay, and also I encourage you to discuss your project and find your teammates for this course.
誒
Okay, let's go.
捉咗10張佢咯。
你開住份通宵，
但係呢個 WiFi 咁樣喺度用。
因為唔做熟，要
係係，呢個仲
一做
我諗佢而家仲熟緊。
佢冇講過我哋係咪照舊一個編程開始。
完全一個想我哋傾下 project。
So when you finalize your text corpus, please upload it here and change the code of the training of the BPE training. So these are the code for training the corpus. You can find it. So in the Copra, you can just change the text here, and you can try to learn change the vocab size in here. So this is a not very difficult, I think, reasonable task. So changing the vocab size in here in the EPE training and add a text in here and remove the standard comments. So I will do one example. Okay. So I will train a corpus for cybersecurity. Maybe I will even train a tokenizer for. It actually works also in binary, so machine code. Okay, so now I found a cybersecurity corpus. So what you will be working in an actual project is find a related text, not I think this would be So these are some kind of corpus that you can directly get it from some source. You do not need to worry about all the encodings because the tokenizer will help to work that out for you. Okay. So once you have this kind of corpus, you can save this corpus, call it like cybersecurity codes.
大陸女仔，嗰個最高人工。
本身話女人，但係後尾即係話啲氣氛又唔同。
佢好似係為咗保護大陸市場先。
大陸市場都冇特別支持，
係
但我就話如果唔係冇用嘅。
Okay, so now I have this corpus. What I need to do is only offload to the server, upload to the HPC server. So remember to put the text in the correct place. It is in sample corpus, and just drag and drop. So after I drag and drop it here, I can go to lab 1 side and change the code. So change the BPE trainer. The comparison hyphen is just to kind of lower the comparison test against the GPT-2 tokenizer. So for this BPE trainer, I can just remove it and add my own. So let me go to here and so when looking into the code, it's the only part that you need to change is the corpus text, because I've already created all the comparison charts and so on. So you need to find the name of the file and update it.
唔可以講你。
So I need to change the PE trainer. And let me find the control text that's loading the file. So in here, sample corpus, I can actually remove all these and then change it to my cybersecurity corpus. Vocab size, I can keep the same. If you want to increase the vocab size, please feel free to try to the comma. Oh, okay. Actually, I think it will work with the comma, but yeah, I think you might want to remove the comma yeah, I think we need to remove the comma. Okay, so please just comment out the code and then I will try to run it.
貼畫。
跟住再，因為其實都係想同樣開始
Okay, so let's see Yes, I think it's- Okay, done.
一張紙
應該就係想俾我哋應該放晒落。
So you see there are cybersecurity
冇講火
focus
罰喎，淨係講時間。
from 10 K, I think, from 100K to 10 to I think 30 to 50. So
10點
you
半
can
飯
download it to see the results.
今日係最後1分鐘，成本感早餐。
哦，你係係喎，你
做咗幾分鐘啫？係啊，都係晒。
正之前。
食到係早餐最後，跟住我聽。
因為食晏晝食焗豬扒飯。
Okay, so this is the cybersecurity corpus for I think 10K. Let's see the 100K.
我哋
So
開頭單集翻嚟嘅，其實即係呢集
so here are the
呢集翻嚟
results.
咧應該
100K, the lower bound
揼晒
is
所
similar
有咁樣，
to
都係只不過係放喺
GPT-2,
度温
and
温完之後有啲嘢出嚟。
即係將啲比較。
for the
GPT-2
top
嘅比較。
12 improvements,
咁揼好咗
I think in here, I think we tie break with the GPT-2. Take 3 tokens for the attention mechanisms. Okay, so this is just a very simple demonstrations on how to train your custom tokenizer for your own niche. And you can actually look into the JSON.
但係有時訓練喎，係咪已經訓練咗？
Okay, so I think it got all the vocab,
精
all the vocabs are in here, all the characters are in here.
定係呢個 server
Let me see if any of this,
我哋等翻 execute
all the capitals are in here,
但係佢唔係就話要訓練
characters are in here.
GPT-2 比㗎。
Okay, we have this special token of dot 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 dot. I think because I'm copying out of the PDF files, and you can see it have some sort of special tokens to parts. And also another tokens for dots. Okay, and also another tokens for dots. Okay, and you can see the merging sequences of how the actual tokenizers merges each word. Okay, so I think, let me see if I'm running. So I think no one is running any jobs at the moment. Okay, so maybe I will let you to run the lab in this week, and I hope you all find a niche that you will be presenting in your project. So I think that's it for today. So any questions? Okay, if no, I think you can go now, and if you have any questions, please feel free to ask. And I hope that by the end of this lesson, you should train your own tokenizer. Okay, but I'm seeing none of you submitting your job. So, anyone successfully trained a tokenizer today? No? Okay, anyone know what a tokenizer is? Okay, okay, good. Anyone know what the task is for today? Today we should be training our first tokenizer. Okay, but if you find this too difficult, please ask questions, and I'll be here taking questions.
問下佢點為之 train 嘅呢做簡單啲。
No, are you guys struggling or confused or? Let me check.
舉個手係數。
Okay.
應該我唔覺得我 train 到咁多，即係我都唔知。
train 個步驟喺起快咯。
係咯，我有個叫 trainer 嘅，
係啦，你應該温咗佢個清單快咯，先清。
但係個 token size 會好大。
有個 BP 都要 trainer。
係啦，我懷疑係頭先温嘅時候要温。
但係咁如果我哋要做我哋自己嘢嗰時候，我哋點樣利用？
即係我
唔係好明呢個係做乜？
一個字一個會變咗。
嗰度 fit
你上面輸入嘅翻嚟，
一般嚟講，
變咗咁樣。
上邊就係輸嘅，下半就係翻嚟。
不過如果你個 set 個 token size 夠大嘅話，係。
係咯，正常。
咁因為呢個 token size 係啱嘅，即係如果你可以 set 到，你可以 set 呢個係10 word 可能係10 million， 即係如果你去到真係啲 large 嘅。
14號21號有。
即係佢呢個係 per word 佢係有一個 fixed 嘅 cap size， 但係呢度係你自己 set， 即係你有個 resource 你會去 set。
佢調轉咗。
係我諗下。
唔止一個對呢個，可能係即係佢有啲對可能係成個 term 嘅 set。係即係譬如好似頭先我做呢個 training 啦，佢有呢集咁嘅嘢，咁呢集咁嘅嘢正常嚟講可能少好多個 token 嘅嘛。咁但係如果我一個 token 就已經讀完嘅話，咁係一開始未去到 input 之前，係啊係。transformer 包 tokenizer 係喺佢 train 佢 input 佢未過 input 嘅時候，即係佢未到 input，佢已經將個 context 變咗做一支 token，即係好似譬如我頭先train 呢個 cyber security 咁樣啦，咁我呢一個已經係一個 token，咁但係如果我擺去出邊啲模型嘅話，呢一個佢可能幫我斬開好多字，咁我咪消耗好多算力咯。但係我如果 tokenize 咗呢個嘢之後，我咪可以直接做運算。
即係減低咯，係係
跟住，如果我一開始 train 個 transformer 嘅時候，用嘅數據應該都 tokenize 咗，用呢個 tokenize 咗嘅數據嚟 train。
係。
咁我點樣去 call 今日對，即係我如果 call 得唔好，咪直接對 transformer 都理解呢個字咯。
係啊。
所以其實 tokenize 其實唔一定係 token 與少少嘅。
唔係 token 嘅數量係你轉換由 text 變成 token 嘅數量，即係唔係 token 嗰個 number 個數量，係字嗰個 size 到 per token 嗰個數量。
所以而家嘅數學 model 就係為咗數學。
係啊係啊係啊係啊。係啊。
笠咗佢個transformer 裏面，跟住佢 ratio 可能又重啲嘅，或者佢多啲數據，做多啲唔同嘅數學題，咁為咗落去呢個加深難啲。呢個咁嘅方法做。
OK， 係，但係仲有一個好特別嘅用處嘅 tokenizer 就係去翻。
咁但係我有啲唔明，咁佢呢個 tokenizer 係點樣應用？
Some let me just repeat what we have discussed. We have discussed whether the token size will affect the performance of the transformer. So the token size itself are of course designed by the tokenizer, but we are considering not the actual token size. We are considering, say, the mapping of tags to the token. So how many for one token, what can you express? The number of things you can be expressed by a token. Say, for example, if I do not have a special tokenizer for this corpus, I would have to spend multiple tokens on this kind of text. But in here, I can only use one token to express this part of information. Another very clear usage of specialized tokenizer is, the thinking process of the large language model use a think token, right? So this is actually a special token that forces the large language model to do thinking. So when you view the thinking, when you view the chat, when you are chatting with the large language model, it shows thinking, right? So it is actually done by a special token. Similarly, in the Whisper model, actually every chat model have these kind of specialized token. If you go to Hugging Face, you click any instruct version of the model, say something like so some model instruct or some model instruct or some model instruct, some model instructs. That's actually meaning it used the specialized token to instruct it to have some other behavior. So any specific behavior that you want can be kind of done by special token with instruct. And of course, the most common use case of these specialized tokens is chatbot. So when you use chatbot, there is a user and system and user system and assistant tag. So how do the model actually knows how does the model actually know what you are doing or what you are trying to chat? It's because of all these specialized tokens during training. Okay. So a fairly clear example is the whisper model that we have talked about. We have talked about the So these are the special tokens. So STOEN transcribed, these are the special tokens used by the tokenizer by Whisper. So when you are doing different tasks, you need to design these. So these are arbitrary tokens that you need to. So say when you are training a robot to view the world and you want to perform a specific task, these are the controllers that you have. So the tokenizer allows you to have these kind of special tokens that your model can train on. Okay.
How to train this kind of
Oh, it's just the tokenizer. So the question is how to do it like Whisper. So the trick is set an SOT token in the BEA tokenizer. After this, during training, you need to add the special token in your corpus. So you need to actually ask, like if you design an SOT, if you want your LLM to behave differently, you need to add these in the training data. When the tokenizer passing your training data, it will already convert this term into a special embedding, which allows the model to perform differently or to behave differently. So these examples is when the tokenizer of Whisper actually look into the raw data, it will read this token and behave differently. So it will determine whether I need to transcribe or translate or what language am I handling, and also where is the whether I should output timestamp or not. It's all controlled in using tokens. Yes, so if you want to train a large language model with thinking ability, you need to add a thinking token. Okay. And if you want your model to have a chat ability, you need to add a chat token. Every chat model adds this token, but they just don't tell you that they add the chat token. So, okay, so the chat token looks like this one. Okay, if you are curious of what the chat token looks like. I thought you learned this in last semester. So this is for system prompt chatbot. You need to add this during training, but of course, yeah. Feel free to take pictures, but you can design these tokens your own. Do not have yet. You can follow the open source standard, but feel free to. Yeah, you can design your own standard. Yeah. So when you are actually sending the API, the request to the API, the JSON that you send to the server will convert your JSON using these tags. And also MCP tools, right? You can have MCP token tools. All large language models use this kind of method to perform behavior, perform differently. Yes. Okay. So I think I missed a very important point here. all of these should be one token. Do not break this down into two, because if you break this down into two tokens, it will not work. It must be one token. Okay. So all the hidden methodology of why agentic AI works are because of these tokens. So this, you put the system prompt into it. For user, you put like, hi, how are you? Something like this, hi. And the assistant will say like, how are you? It's all trained them. So when you train your own chatbot, you need to add this token. That's why it is important to make your own tokenizer if you want to train your own chatbot.
I think this kind of work is building system.
Oh, okay. Yeah.
一次知道原來
係啊
佢自己有個 system，我 break down 咗自己升級嘅 LA。
Okay, so I don't know whether you have noticed, they actually, when I click text generation, they specialize, say instruct. They will clearly state their tokens. Start of text, LM start, and then system. So these are particular important system for this model, right? So each model have their own way of doing tokenization. You see, tool call and then get candidate. So it's exactly the same as this one. So IM start assistant, IM start tool. But of course, you can design your own token. So the first step is to design your tokenizer. That's why I want you to design your tokenizer today, because it will affect the rest of the course. And you have to think about your project, whether to do a chatbot or to do a chatbot with tools. And you need to design these before training anything. Okay.
Train the specialized trainer
So, any more questions about tokens and
所以我
tokenizer?
下面寫咗咯，佢話咩要係 one check token 所以我未理解到，但係我翻進入邊咗先打，係我哋理解到嘅時候，你就會理解到㗎啦。
唔係，佢如果見到呢個，佢會即刻認識呢個 token。因為你個 tokenizer 已經係
可能係教點樣讀個 token，佢可能
most frequent 嘅 text， 即係根據我哋頭先個 algorithm，most frequent 嘅 text 會係個 ID 會係越早嘅。
即係會唔會係佢以前個 token 跟你編咗佢，你跟佢設法。如果唔係咧，就佢用佢設法咧就好普通。你整個 efficient
但有幾行我唔好明。啱啱打
因為
幾好難嘅，又
係咩 system？
其實係睇晒成篇文數 frequency， 即係佢唔係stop， 即係佢唔係 stream 咁樣做嘅，係佢係睇晒所有字再 compute 個 frequency 再做。係啊，做。係啊，佢要睇晒，佢要嗰個 tokenizer 係要睇晒。So I think I will test your understanding in the next lesson to see if you understand what I meant by token. Okay. So I think some of you do not get what I meant by tokenization. But I think we will see for next lesson. So that's it for today. Okay, see you next week.